paraphrase Taylor Swift, it's me, hi, and I'm the speaker. And I will talk about model transparency for model AI, ML security. So as you know, this is a talk about AI. You've heard a lot of talks about AI. I will use AI or ML interchangeably. I know in theory they are not the same. AI is larger than ML, but for the purposes of this talk, let's just consider them the same. And just for contrasting, the software that doesn't use AI, let's call it traditional software. And now if you look again at the Venn diagram between the two, you see that there are some things in common. So let's focus on those. One of the things in common that we want to focus on is the history. Both traditional software and AI-based software started first as hobby, as research. People in academia built computers. Internet was built in academia to connect several computers and so on. And then it became commercial, then became a commodity. People can use it. The same happened with AI, but just at a much faster pace. So first we had people in academia doing research with AI, trying to understand which images were dogs, which images were cats, and so on. Then you started having some commercial uses for AI, like the Google Translate, like applications like this. And now with the ChatGPT and so on, you started having AI as a commodity. So everyone can start using AI. Everyone can start building their own GPTs and so on. Actually, the history goes a little bit more. As the application started being more and more mainstream, you also started having more and more hackers and more exploits and more cybersecurity incidents, both in the traditional software and both in the AI. And now let's give some examples for exploits in the AI. Let's just focus on GPT-based models. So we know, for example, that you can build an evil model where you hide some malware inside a neural network. This is because most neural networks are actually Turing complete. The framework that implements them has operations to write to files, to send network packets, and so on. So you can encode your malware inside a big LLM, and then at some point, if a specific prompt is given to the LLM, you can trigger that. And because most models are opaque, nobody can know what's happening. And there is also the possibility to build like a GPT 4chan, where it's a GPT trained in 4chan, and it's going to still act normally, so still give you text for text, not do anything malicious, but the text that is giving back to you is bad. And this is not just theoretical, just research. We have also seen it in practice. So we have seen ChatGPT being poisoned. We have seen poisoned GPT that has been actually published on Hugging Face to spread fake news. And this becomes even worse when you start using AI to build more software. So we have GitHub Copilot that generates code for you. What if GitHub Copilot were to be hijacked? And now it generates code that contains malicious users, and then somebody can exploit this. Or even worse, there is, for example, a demo GPT that builds a prototype of your app in minutes. You just describe what the app should contain. Demo GPT builds it entirely for you. You can even deploy it if it works. And in most cases, it works. And this is not just commercial users. This also affects high-performance computing. So SPAC, the package manager for high-performance computing, now uses LLMs to try to guess which packages should be updated first, such that the entire update plan won't cause issues. So now if the LLM gets confused, the entire cluster can be brought down. OK, so we need to merge security and AI together. And actually, there are several ways in which you can fill the gap. We can have security from AI. We can build applications that are secure against whatever malicious an AI can build to us. Or we can bring security via AI. We can build applications that, for security that are powered by AI. For example, there is Socket that uses LLM to understand obfuscated code and tell you if that obfuscated code is malicious or not. And there is also security for AI, where we try to bring security for deploying AI models and so on. And basically, that is what I want to focus on during this talk. And the motivating example is this scenario that happened some months ago. Attackers were able to find out several terabytes of data used by Microsoft AI researchers. Data as data, they could manipulate that and so on. But what was wrong, what was worse, was that in the buckets, they could also see ML models. And since a lot of the models are pickle files, and again, they are not easily inspectable, somebody could maliciously modify the pickle file, and then later when you want to use the model, anything could happen on your system because now it's no longer doing no longer just an ML model. Okay, so let's look at another example. This one a little bit more theoretical. So let's consider Kaggle. And let's say I'm a bad attacker that I want to exploit Kaggle. And I train two models. One, it's evil model, and the other one is the GPT-4chan that we have seen previously. If I upload them to Kaggle, in the model card, I will have to put a description. Of course, I can put some fake descriptions, like I could say that evil model actually detects malware, and the GPT-4chan is a friendly chatbot, and publish them like this. And then I hope that users would download them, would use the models, and then I would exploit the users later. Of course, users, if they see the name evil model, probably they're not going to download it, or they're going to sandbox it. But I can always rename the model. So instead of evil model, I can say it's a nice model, or instead of GPT-4chan, it's a GPT-4 friend. And now users are going to say, oh yeah, it's a good model, especially if I do a lot of advertising and a lot of promotional material around it, users are going to deploy it and use it. So the problem is that on their own, the models are not publicly attributable to the user. So I can exploit thousands of users, and they could say, oh, we detected that this model is malicious. It's OK, delete the model. I upload a different one. Nobody can attribute that to me. Nobody can detect all of the models that I release are bad. So to solve this, we actually need to look at the entire supply chain for building a model. But basically, we should protect the entire ML supply chain. What is the ML supply chain? Let's think about what we need to do in order to train a model. First, we do some data set preparation, we do some model training, and so on. Now that we have a model, we publish it somewhere such that users can then use it in their applications or their experiments. So there are 3 pillars. And if we zoom a little bit more into that, let's say now I'm an ML developer and I want to build a model. The first thing that I do is take some data set and pick an ML framework and split the data set into the training test and the test set. So here I just picked TensorFlow, but doesn't matter, I can pick whatever. So I already have some inputs, the data set and the ML framework. The next step that I do is I pick a model architecture and I code it in the ML framework of choice. So like a sequential model in TensorFlow with Keras. Doesn't matter, the model is the data set and the architecture. Now I need to combine these pieces together and do a training. Once I train the model, I publish it to some model hub, then I wait until somebody downloads it. And once somebody downloads it, they use it in inference for their products, and now I can exploit the model. If the model was malicious, I can exploit the user. This diagram here looks very similar to the diagram for traditional software. I just switch the labels. So a developer has a source repository where they write the code. This code uses some dependencies. You put them together. You get a build for an artifact. You publish this artifact somewhere and wait until somebody downloads it and uses it. So if we squint a little, we could say, maybe we can do make my model, or Bazel build my model, or whatever build system you want to use, my model, and treat training a model the same as building a normal software. And going by this analogy, even the attacks that we have for regular software, for a traditional software, they also apply for models. So an attacker can compromise just the model hub. So I trained the model. I was OK training the model. I didn't do anything malicious in that. I upload it to a model hub, and then the model hub gets popped, and somebody manipulates the model there. Or I publish the model in some cloud bucket, and then that cloud bucket gets accessed by external attackers, and they modify the model. Or an attacker can be even more malicious. They can try to exploit the training process itself to inject bad behavior during the training. I can also be wrong myself. I can either use a dependency that has a vulnerability, and then the attacker can exploit that, or by mistake, I can submit bad code, and the model that I train is bad. So there are multiple possibilities in which malware can be ingested in a model. And now, protecting the supply chain means putting bubbles around parts of this to protect them. So let's start with the simplest one. Let's say I train the model, and now I want to be sure that after this point, nothing can happen to this model without me knowing. Or the users of the model would know that something happened to the model since I last trained it. So in order to do this, we are going to use a solution called signing, the same as in traditional software. You build your software, you sign it, and then users would verify the signature before using it. And for signing, we selected Sigstore, which is the same as Let's Encrypt for software, but for software artifacts. So the process that we want to do is, let's say I'm the model trainer. Nice. I'm the model trainer, and I train the model, and then in my code, when I do model.save, instead of just writing the model to disk, there is the signing flow that happens behind the scenes. So this signing flow would get my identity, for example, my GitHub username or my email, and so on. There will be like a pop-up to select which identity I want to go. We'll go to Sigstore CA to get a certificate. And then we'll use this certificate to sign the model and put the signing event into a Sigstore transparency log. And return to me back, OK, the model has been inserted into the transparency log. Here is the here is the path in the Merkle tree. Now I can publish this model to the model hub together with the transparency log, with the proof of including in the transparency log. And then the model hub itself can verify, OK, this model has been signed. I verify the signature. I can put it in the model card associated to the model. I can put a label that says, this model has been verified. You can trust this. It's not a malicious model. It's not a model that has been just bumped over the fence and nobody cares about it. And then later, when users want to use the model, they can either trust the model hub, the badge there that says verified, or they can run the verification process themselves. And signing and verifying the models is quite fast, so scales very well. So we tested from small models all the way to big LLMs, and we never had more than 10 seconds to wait. OK, so this solution only helped the compromise of the hub. But what if we want to protect the entire supply chain? What if we want to record what was the source that has been used to train the model? Or what if we want to also record the databases that have been used in the model, or the ML framework? For this, we're going to use another solution for the software supply chain called Salsa. Salsa basically generates a provenance file associated with the entire build process, or train process in this case. So what we did was we added GitHub Actions, where you can trigger the GitHub action. You can say, I want you to train a model and generate provenance, and this is the format for the model. So here, for example, I can pick Keras model for TensorFlow. But actually, we support both TensorFlow and PyTorch, and other models can be supported in the future. OK, so at the end of the GitHub action run, we get two things. We get the model, and we also get this JSON file that is the provenance. And people can look into the provenance by themselves, or they can run a Salsa verifier automatic command and verify with that. Let's look at the provenance manually, just to see what it contains. So if I cat it and pipe it to JQ to see what the JSON contains, I see that it has some signatures, so nobody can change the provenance after it was generated. And it also has a payload, which is base64 encoded, so next step to do is to look into the payload itself. So if I look into the payload, first it contains a field called subject. This subject is actually the model that I trained, and it also has a checksum. This checksum should be exactly the same that you use during the signing and during the signing flow with Sigstore. If we look more into the payload, we see that we also have a builder, so basically the trainer for the model. And here we can record, like, you have used this code, you have used this training framework, you have used these databases, and so on. We can also record them in the materials portion. So the materials are more, if you think of Salsa like the recipe for cooking something, the materials are the ingredients, and the builder is how you combine them together to get the final product, the model. And in our case, for materials, we just record the repository with the commit. But this should be enough to see exactly what has been used to train the model, because the entire code for downloading the data set and so on is in the repository. And all of this can be automated, so Salsa verifier can look into it and verify the provenance, or in case you have a model that you have trained for hundreds of CPU hours, and then you discover, okay, the framework that I have used has a vulnerability, and now you can decide, do I want to spend hundreds of CPU hours to train all of my models, or I can look into this provenance and identify exactly which models have been trained with that vulnerable framework, and only train those. Okay, so in the future, this is still incipient work. So in the future, we still have to do, on the model signing work, we want to increase performance of hashing. We want to make it as fast as possible, so basically users won't notice any delay at all. And we want to integrate it with more ML frameworks, so instead of users having to save the model and then sign it, we want the entire flow of model.save, do the signing, and so on, as I was describing on the previous slide. And also the integration with more model hubs and model cards. So if you go on Kera, if you go on Kaggle, if you go on weights and biases, wherever you go to get a model, you would see the verified badge. On the Salsa side, we want to scale it outside of GitHub Actions. So for example, using Tekton if you train on GCP or on AWS. We also want to support TensorFlow saved models or very large models which split the weights into multiple files. Because right now, Salsa verifier only checks the checksum. So if you, sorry, if you have multiple files, and I flip the order of 2 files, now the model no longer behaves properly. But Salsa verifier will still see all of the checksum that it was expecting. So it will say, yeah, the model hasn't been tampered with. So this is something that we have to work in the future. And as I was saying, we also need to record the dataset provenance. We want to know exactly what data has been used in training the model, maybe exactly what images have been used, and so on. And there are other standards in supply chain that you can also bring to the ML world. So for example, there is SBOM, Software Bill of Material, which just records each dependency, which their hashes, and so on. And on the vulnerability side, there is a VEX standard, there is a CVEs, and so on. So you can imagine bringing those two to the ML world. But the conclusion is that we can bring the same protections from the traditional software to the ML world, and we don't need to reinvent the wheel just because ML is so popular right now. And finally, on the last slide, I'll have 4 QR codes. The first one is to the repository, where we have the proof of concept so far. The second one is a blog post about this. Then the third one is an OpenSSF, Open Source Security Foundation, working group on AI and ML, where we can discuss these topics and other similar related ones. And finally, the last one is from Google Secure AI Framework, which is the framework that encompasses this work, plus work on alignment and privacy and so on. And that is all. Thank you very much.